Hi, this is Wendy Peel with Texas Instruments, and today I'll be going over an introduction to stoichiometry using the Science-inspired lesson titled Solving Stoichiometry Problems. This lesson and many more are available for free at www.scienceinspire.com. You can use these lessons with the TI-Nspire CX Graphing Calculator, the TI-Nspire iPad app, or the TI-Nspire teacher or student software. Before we begin doing some stoichiometry problems, you may be asking yourself exactly what is stoichiometry and why in the world would we need it. Stoichiometry is simply a process using a balanced chemical equation to calculate the amounts of products and reactants. In other words, just a technical way of saying you're using ratios from the balanced equation. Before we get into the process and calculations of stoichiometry, let me give you an example of how you would actually use stoichiometry in your everyday life. Say that you have your grandmother's favorite oatmeal cookie recipe, and the recipe calls for 2 eggs to be used with all the other ingredients, and that's going to make 2 dozen cookies. That's an easy one to follow because you've been told that exact amount in the recipe. What if you were hosting a large gathering and needed to make 8.5 dozen cookies? You would need to calculate how many more eggs you would need to make this many cookies. This calculation process is called stoichiometry, but in this activity, we will be doing problems involving chemical equations and compounds. In other words, stoichiometry is also known as chemical arithmetic. So let's get started. In today's activity, I'll be using the TI-Nspire CX Premium software, but this activity can also be loaded onto a TI-Nspire CX Graphing Calculator, as well as the TI-Nspire iPad app. I have the activity pulled up on the screen with the TI-Nspire CX Premium software, and as you'll notice, there's some page numbers at the top left of the screen here. Those are the different pages within the activity. I'll also be using a few of the buttons over here on the keypad so that you can see, if you're following along with your graphing calculator, you can see which buttons I'm pressing as well. In order to go between the different pages, I can either move my cursor here to the next page and click and select that, or I can do Control and then the right arrow on the keypad, and it will take me to the next page as well. In the first problem that we'll start with, we're going to have methane react with oxygen to yield carbon dioxide and water. The main thing you need to remember when doing stoichiometry problems is that you must begin with a balanced chemical equation. If your equation is not properly balanced, then you will not be able to do the calculations to generate the correct answers. According to this equation, looks like I'm going to need, I have 4 hydrogens here, I have 2 here, so I'm going to increase using the sliders here. I'll use the slider to increase it to 2, so 2 times 2 is 4 hydrogens there, 4 hydrogens there. I have 1 carbon here, carbon there, but I've got 2 oxygens here, and I've got 2 here, and then 2 times 1 is 2 there. So I've got a total of 4 on this side, but only 2 on this side, so I'll need to increase this slider to 2. But don't forget, there's a 0 in front of this when we're using these sliders, so because there is a carbon there, I need to actually increase that to a 1 and also increase this to a 1. So let's double check and make sure we're balanced. I have 1 carbon on the reactant side, 1 carbon on the product side. 1 times 4 is 4 hydrogens. 2 times 2 is 4 hydrogens. 2 times 2 is 4 oxygens. I have 1 times 2 oxygen, part of carbon dioxide, and then 2 oxygens, part of water, which is a total of 4. So we have a balanced equation. Now that we have our balanced equation, which is telling us I've got 1 mole of methane reacting with 2 moles of oxygen to yield 1 mole of carbon dioxide plus 2 moles of water. These numbers out in front are known as our coefficients, if you'll remember in your balancing equation unit. Now we're going to take those numbers, those coefficients, and use them in a ratio form to do stoichiometry to determine if I start out with a certain number of moles of this and react with a certain number of moles of this, how much would it produce of our products on this side? Or if I start with a certain number of moles of methane, how many moles of oxygen would I need to produce a certain amount of our products? So the first example I'm going to use is going to be very simple, straightforward. We're just going to use 1 mole of methane. So if I start out with 1 mole of methane, well, that's what I have right there. This little simulation here is going to say, okay, well, if I've got moles of reactants to moles of products here, what am I going to need? So if I click play using 1 mole of methane, I'm starting out with 1 mole of methane with 2 moles of oxygen. Okay, so if I react 1 mole, I'm going to need 2 moles of the oxygen to yield 1 mole of carbon dioxide and 2 moles of water. So that's a very simple one because that's straightforward based on the balanced chemical equation. Now that you've seen that example, let's try another. We started out with 1 mole of methane, so let's decrease that and let's try 0.5 moles of methane. That's half the amount that we used before, which, looking at the equation, you should be able to understand that you're going to produce, for if I have half a mole of this, then that means I would have half of this, which would be 1. I would have half of this, which would be 0.5, and then half of this, which would be 1. So let's see if that's what happens. So 0.5 of this, 1 of that, which is half, will yield 0.5 of carbon dioxide, which is half, and then 1 mole of water, which is half. So those are easy when you're using easy numbers like 1.5, 1.5, and whole numbers and things like that. So let's go to another problem and some other examples, and let me show you how you will do actual calculations to do stoichiometry on this. I'm going to move to page 1.3, and let's see the question here. How many moles of water are produced for every mole of methane? And also, what is the mole ratio? So back here it asks how many moles of water are produced with every 1 mole of methane. So that means 2 moles of water are produced for every 1 mole of methane. So that is a 2-to-1 ratio. So I've inserted a new page and I have copied the balanced equation over to this page so we don't have to keep going back and forth. But what we're going to do, instead of just watching the simulation to give us answers, we're actually going to calculate a different example, and then we'll go back and check our answers on the simulation itself. So instead of using 1 mole of methane like we did in the previous example, this time what if you had 0.2 moles of methane that you were beginning with, and we wanted to convert and see how many moles of carbon dioxide we would get and how many moles of water we would get. So what we're going to do to start with is I've started out with 0.2 moles of methane, and that is a 1 right there. So remember our coefficients, that's what we'll be using in our mole ratios. Okay, I'm going to multiply that by the mole ratio. Anytime I'm going from one side of this equation of my reactants over to my products, to get over there to make a conversion from methane to carbon dioxide, I have to do it through the mole to mole ratio using those coefficients from your balanced equation. This is why it's very important that if you don't have your equation balanced properly, then your answers are going to be off. Okay, so what we'll do is we're going to do a mole to mole ratio. I need to get rid of the moles of methane unit is what I need to get rid of. So I'm going to insert using control and then the division sign to get me a fraction template. So if I need to get rid of moles of methane, then I would need to have moles of methane on the bottom in the denominator of my problem here. So I'm going to put moles of methane, and then I'm going to go into the catalog key to get my actual subscript. Okay, and I'm going from moles of methane, and it's telling me to go to moles of CO2. So I'll type in moles of CO2 in my numerator, go back to the catalog and grab that 2 subscript. Now I need to look at this and determine what are going to be my numbers for my mole ratio. Well, according to the equation, for every 1 mole right there of methane, okay, we're going to have 1 mole of carbon dioxide. So that would be a 1-to-1 ratio. So I'm going to type a 1 there. Now, based on this, just on simple arithmetic, when I am looking at this, and I'll show you one example this time, and I probably won't do it anymore after that, I'm going to format this. Okay, so I'll format my text, and I'm going to strike through that because that unit right there and this unit right here, once you do the calculation, then they will cancel each other out. Okay. And then that's going to leave us with moles of CO2, which is what I was asked to calculate for. Well, obviously 1 divided by 1 is going to be 1, so you multiply everything across and divide by everything on the bottom. So 0.2 times 1, that's going to equal 0.2 moles of CO2. Go get my 2 subscript, and that would be your answer. All right, now we're going to do the same thing, but for this one, we want to know how many moles of water will be produced for this particular example if we start out with 0.2 moles of methane. Well, if I had 0.2 moles of methane, and there's a 1 associated with that, there's a 2 associated with oxygen, which is what we're going to start with on this one. That is a 2 to 1 or 1 to 2 ratio there. Okay, so if methane is 0.2, then obviously oxygen has to be double that, which is going to be 0.4. So that is why I started out with 0.4 moles of O2 and not the 0.2 moles of methane, because we don't have 0.2 moles of methane. We have double that for oxygen. Same thing here. I'm going to insert the template for my fraction. Okay, on the bottom, I need to get rid of this unit, so that one's going to be on the in the denominator there. So I need to type moles of oxygen and go grab my subscript. And then obviously it's asking me to go to moles of water. Okay, so if I go to water, oops, in the wrong spot there. Okay, so moles of water. And then I need to look at my ratio to see what numbers I need to use. So in my equation, okay, I go back, when it's the moles over moles for that mole ratio, I have to use my coefficients. That's the only numbers you use when it's this ratio of mole over mole. Okay, so I'm going to go from moles of oxygen, which is 2, so that's going to be right here in our denominator, and I'm going to go to moles of water, which is also 2. Well, that's basically the same thing as saying that's a 1-to-1 ratio, is it not? Okay, and because of that, then my answer would be 0.4 times 1, so that's going to be 0.4 moles of water. And I'm just going to Control-C and Control-V right here. That's the beauty of the Nspire, is you can do Control-C and Control-V on your computer as well and on your handheld. Okay, now I'm going to go back to the original page of the simulation, and we're going to check our answers against this beginning value of 0.2 moles of CH4 to see if we do come up with these particular answers we have right here. So let's go back, make sure my equation is still balanced properly. It is, and I'm going to start out with 0.2 moles. If yours is not on that, just use your sliders to change it to 0.2 moles of methane. Okay, and then I'm going to click play. So there's the 0.2, and there's where we started with 0.4 moles since it was double of oxygen there. And we did come out with 0.2 moles of CO2 and 0.4 moles of water, which is what we came up with in our answer. So basically what you're doing in these problems is you're taking what's given with you on one side of the equation, whether it's the reactant or the product, and you're converting to one or the other on the other side of your equation. And you're going to do that through the mole-to-mole ratio using your coefficients in your balanced equation. Okay, now we'll look at another problem, maybe a different way you might see your question asked for these particular calculations. I'm going to use the same equation before we switch to a new one. So the first question is, how many moles of water are produced for 0.3 moles of methane? So it's asking me for how many moles of water are produced, and we know it should be produced is the key word because that is one of our products, for every 3.3 moles of methane. So this is the number I'm starting with, so 0.3 moles of methane, so I've already got that one written down, and I need to convert that to moles of water is what it's asking for. So once again, I need to do that through the mole-to-mole ratio. Remember, if I'm going from one side of the equation to the other, I have to do that through the mole-to-mole ratio. So I'm going to go from moles of methane to moles of water. So let me get my template. If I'm getting rid of moles of methane, I need to be able to divide that out. So that's going to go in the denominator. So that's moles of methane. Okay, and I'm going to moles of water. Okay, now once I've got my units here that I know are going to cancel out, then I need to get my actual coefficient numbers for the ratio. So for every mole of methane, so that's 1 mole there, And the ratio of methane to water, the coefficient for water is going to be a 2, so it's a 1 to 2 or a 2 to 1 ratio. And based on that, if I'm calculating 0.3, multiply everything across the top, divide by everything on the bottom. These units here, I'll do it one more time here, just for time's sake here. If I cancel that out, because numerator and denominator units will cancel out. Okay, so those would cancel each other out, leaving us with moles of water, which is what it asked for. So that is going to be 0.6 moles of water. And I'm going to go back and cut and paste to save some time. Okay. Now, the next question looks very similar to the previous one, but you have to be careful in these problems that you're really looking at what's being asked for. I highlighted the words in blue on this particular problem just to call it out a little bit quicker to you. This one is saying how many moles of oxygen are consumed, meaning how many moles of this are going to be used up in order to produce 1.5 moles of carbon dioxide. So even though I'm starting with a value associated with a product, I still can go back and figure out how many moles of one of my reactants were needed to get that many moles of our product, okay? So you still go with what's given to you in your problem, which was 1.5 moles of carbon dioxide. Start with that. Okay, I'm going from carbon dioxide to oxygen, so I'm going from one side of my equation to the other, so I have to do that through that mole-to-mole ratio. So get my template again, getting rid of moles of CO2, so that's going to be in our denominator. Okay, and I'm going to moles of oxygen. All right. And then once we have this, we look at our ratio, and per my coefficients in my equation, I've got 1 mole of CO2, so that'll be a 1, and then my oxygen, I have a 2, so 2 moles of oxygen. Okay, the moles of CO2, that cancels out as far as units go, which is left with us calculating 1.5 times 2, which is going to be 3.0 moles of, just do it easier here, moles of O2. So once again, whatever is given, value is given to you in the problem, write it down first, then see what it's asking you for, and if you want to put a question mark over the product or reactant it's asking for, so you can see where you start and where you're going to, sometimes that helps as well. Now we're going to move on to a problem that's going to be a little bit different. The problem we worked before was going from moles to moles, but this time we're going to actually use an equation to where we're going to determine a mole to mass conversion to calculate the mass of our products for a given amount of reactants in moles. So in other words, it's going to ask us, it's going to give us a number of moles of one or more of our reactants, and we're going to be asked, if we start with that many moles of that reactant, how many grams of one of our products would be produced? Well, in order to get from moles to grams, you have to go from a moles to a mole-to-mole ratio before you can get to the grams. So I'm going to show you that. That may be a little confusing just hearing it, so I'm going to show you an example. But let's just look at the simulation to start with. The first thing we have to do, though, is actually balance our equation. So let's do that real quick. Okay, so we'll start the simulation. I have used my slider to increase my moles of ethene to 1. So let's see what happens. And remember, you have a 1 to 3 ratio of your reactants here. So that's what we should be starting with. And we're going from moles of reactants to grams of products. So I'm going to start with a 1 to 3, which is what we said in the equation. But then it's going to go over here, and it's asking us how many grams of CO2 are produced and then how many grams of water. So it doesn't give us an answer here. We're going to have to calculate that. Okay, through the magic of technology, I have gone to the next page, and I have already balanced this equation, copied and pasted it over here. I already went ahead and did the calculations for us here just to save a little bit of time, because half of the problem you already know how to do based on what we did previously. So I've taken my balanced equation here. The example we're going to be using is the one that we had on the simulation, so that we can run that same simulation and check our answers. Is we're going to start with 1 mole of ethene. okay, and we're going to convert to moles and grams of CO2. All right, so the first step is how many moles of carbon dioxide will be produced in this reaction. So I'm going from moles of something on this side to moles of something on this side, which means a mole to mole ratio. Remember I said if you go from moles of one side to moles of the other, it has to be through that mole to mole ratio. So I start out with the 1 mole of ethene, which was right here. Okay, I need to get rid of the moles of ethene, so I'm going to put that in the denominator. I'm trying to get to moles of CO2, okay, which is what it's asking for there, so I'll put that in the numerator. Mole to mole, anytime you have mole to mole with each other, you're going to use that ratio by finding your coefficient. So I need to find the coefficient for ethene, which is 1, and my coefficient for carbon dioxide. So I've got 1 mole of ethene to every 2 moles of carbon dioxide. Multiply straight across. These units here cancel out, leaving us with moles of carbon dioxide, and I get 2.00 moles of carbon dioxide. Now the second thing it's asking for is grams of CO2. Well, right now, the only thing I have is moles of CO2. Okay, so that's the only thing I can continue with. At least I'm in the correct compound of CO2. I'm just not in the correct unit of grams. So I'm going to take this 2 moles of carbon dioxide and move it down here. Okay. All right, so that means I need to get rid of moles of CO2 because I want grams. So anytime you want to get rid of a particular unit, it needs to go opposite. So if this is in the numerator, it's going to go in the denominator now. So I'm going to put that on the bottom. Now I'm going to go to grams of CO2. The way you calculate when you go from moles to grams is that you're going to calculate the molar mass of your compound. All right, so the compound we're working with is carbon dioxide. So there's 1 carbon and there's 2 oxygens. Now you need to go to your periodic table and find your molar mass or your atomic weight of each of those elements. So with carbon, it's going to be, actually this particular activity only wants us to use 3 sig figs. Go by whatever rule your sig figs that your teacher requires you to use. Okay, so we're just going to use 12.0 for the carbon, and we're going to use 16.0 for oxygen. Well, there's 2 of those, so that's 32. There's 1 carbon, which is 12. Add those together, and we get 44.0 grams of CO2. Multiply straight across. The units there cross out, leaving us with grams of CO2, and that's going to give us 88.0 grams per mole, okay, of CO2. Or sorry, grams, no moles, so just grams. Okay, sorry about that, my mistake. Because this unit, I'm going to show you that, just show you my mistake. I got ahead of myself there. That unit cancels out with this unit. Okay, and when that cancels out, that leaves us with grams of CO2, which is what the problem asked for. So it's 88.0 grams of CO2. So let's go back to our simulation page, and if I type in 88.0, it gives me a check mark, so that is correct. Okay, on this particular problem that we just did, notice that I gave you the problem in 2 separate questions, so that we did 2 separate calculations. I'm going to actually show you how you can do this all in one calculation, because most of the time you're not going to be asked the separate problems like this to give you a hint to go to the moles first and then the grams. You're going to have to remember that you have to go through moles first to be able to get to grams. So, for example, on this particular problem here, same equation here. We got ethene reacting with oxygen to give us carbon dioxide and water. But this one is asking how many grams of water will be produced. So grams of water, okay, will be produced in this reaction with 3 moles of oxygen. So I'm just starting out with the same number of moles that I have in my equation here. So with this one, remember, if I'm talking about a reactant and a product, I'm starting with 3 moles on this side, and I have to get to grams on this side. Remember, I have to go through that mole to mole ratio first. I cannot just jump from moles of oxygen to grams of water. So keep that in mind if I'm going from one side to the other. Mole to mole ratio first. So I gave you a little hint here. You go from moles of oxygen to moles of water, then to grams of water. So sometimes it may help to kind of write this out when you're working through these problems. So I started out with the 3 moles of oxygen already. Okay, I need to get rid of that unit, so I put it in the denominator. And then I've got moles of water, and so I've got a ratio of 2 moles of water to every 3 moles of oxygen. So I need a 3 there. Okay, all right. Now I've gotten rid of my moles units, all right, but I still have the moles of water. That is not what it's asking for. It's asking for grams of water. Okay, I can actually just continue this calculation and keep doing the same thing just with my fraction template here. So I'm going to go to my fraction template again. Now this time I need to get rid of moles of water, okay, and if I'm trying to get rid of it, it's got to go opposite of where it is. So it's in the numerator here, so it's in the denominator here. So I'm going to go to moles of, let's just go ahead and cut and paste that. Let me do that one more time. Sorry about that. All right, so in my denominator, I'm going to get rid of moles of water. Put that in the denominator. Now I can go from moles of water to grams of water. Okay, and I can do that, remember, I mentioned a while ago about using your molar mass. Okay, all right, so the molar mass is going to tell us how many grams are in every mole of a particular compound. All right, so to get your molar mass, remember, do your formula of H2O for water. So I've got 2 hydrogens at 1.01 each, gives me 2.02. I've got 1 oxygen in that formula at 16. Okay, add those up, that gives me 18.0 grams. So that's 18.0 grams for every 1 mole of water. So the molar mass is the mass of your compound per 1 mole. Okay? All right, so now I can actually go and I can actually format that so that you can actually see the final. So I'll mark through that because that unit and that unit cancel each other out. Okay? And once I cancel that out, once I am left with the unit that it is requested, then I can stop and do my calculations. So with this particular one, you're going to multiply 3 times 2 times 18 divided by 3, and that's going to give us 36.0 grams of water. I'm just going to copy and paste again because that's the unit that's left. Do not forget your units with your answers in these problems. Okay, so now let's go back and let's check our simulation to see if we actually, if we start with 3 moles of oxygen in that problem with ethene, if we're going to get 36 grams of water. So when I go back, we're still using the problem of moles of ethene. Started out with 3 moles of reactants. Okay, and if I type in 36.0, I get the check mark. Okay. I could go from 1 mole of ethene over to how many grams of water doing the exact same thing. I would just start with 1 mole of ethene here, put the ethene down here, moles, and then the moles of water here, do your mole to mole ratio, and then go from there and do a calculation. So I could ask you any particular reactant going to a product and vice versa, but you have to go through that mole to mole ratio to get from one side to the other. Okay, last but not least, we've got one last problem here. In this particular one, I've already balanced your equation. We're going to have the combustion of propane, which is C3H8. So you've got propane reacting with oxygen to give us, once again, carbon dioxide and water as your products. Before, we've been going from moles to grams or moles to moles. Now we're going to go from grams of one of our reactants to grams of one of our products. So we're starting out on one side, going to the other, and if you remember each time I've said it, if you're going from one side to the other, you have to go through that mole to mole ratio in order to do that. Now, just like the previous problem that we did before, we're going to have a simulation that's going to show us kind of the reaction that's happening, but I'm going to jump to the next page here in just a second to show you the actual calculations, and then I'm going to let you calculate the final one. So we're going to bump this up to 10 grams of propane, and then I'll click play. So we're going to let it react. And once again, it's going to leave us with those boxes. But notice again, we're going from grams of the reactants to grams of the product. So on the next page, I've got your balanced equation for you, and the question that I'm asking is how many grams of carbon dioxide will be produced from the combustion reaction of 10 grams of propane. Okay, so the path I'm giving you as your hint, okay, what was given to us was this 10 grams of propane. So I start out with 10 grams of propane. I have to get over to carbon dioxide at some point. So going from propane to carbon dioxide, from one side to the other, I have to do it through a mole to mole ratio. So that means I've got to get these grams of propane to moles of propane. Then I can go from moles of propane to moles of carbon dioxide and then convert that to grams. So that's kind of the path I've laid out here. So I started out with the 10 grams of propane, put the grams of propane on the bottom in order, or the denominator, in order to get rid of that with the original 10 grams of propane. And I'm going to go to moles of propane. So I need the molar mass. So I calculated the molar mass to be 44.0 grams. So for every 1 mole of propane, you'll have 44.0 grams. Okay, I canceled those out. I was left with moles of propane. I'm still not in the correct compound. I've got to get to carbon dioxide. So I've got to get rid of moles of propane. Once again, it goes in the denominator. Okay, and then I can do a mole to mole ratio here by going to moles of carbon dioxide. So I put that unit down. Mole over mole, that means go find the coefficients. That's your hint. Okay, so go back up to moles of carbon dioxide. My coefficient is 3. Go back to propane, the coefficient is 1. So that's a 3 to 1 mole to mole ratio. I can now cancel the moles of propane units out on the numerator and denominator. I'm left with moles of carbon dioxide. Okay, I want to get rid of that because I've got to get to grams, so I'm going to put moles of carbon dioxide on the denominator, grams on the numerator. Then I calculated the molar mass. So anytime you've got grams and moles as your fraction here, that means you're calculating molar mass for your grams. So I calculated the molar mass of carbon dioxide here. So this means for every 1 mole of carbon dioxide, I would have 44.0 grams of carbon dioxide. Multiply 10 times 3 times 44, and then I would divide that by 44. Or if you automatically see it and want to cancel out the 44s on the numerator and the denominator, that's fine. And then you would just know just to multiply 10 times 3 to give you 30. Totally up to you how you want to do it. Okay, so now let's go back and check our first answer to see if we get 30.0 grams of carbon dioxide. So if I plug this in and say that I calculated it, it gives us the check mark, which is correct. So now that we've done the calculation to determine how many grams of carbon dioxide are produced in this reaction, I'm just going to give you the answer to determine, to show you how many grams of water are actually produced in this combustion reaction. And hopefully with the examples that I've given you on the page that we just worked on will actually help you to get the correct answer. So that answer should be 16.3. So type that in, get the check mark for that. And then one last thing, this activity as well as many other science content activities can be found at scienceinspired.com. And you can also visit our main website of education.ti.com, where you can find many other math and STEM related activities just like this one that will help you in your studies. So I hope this was helpful, and good luck to you.